Your lecturer is Indre Viscontas. Dr. Viscontas is an adjunct professor of psychology at the University of San Francisco and a professor of sciences and humanities at the San Francisco Conservatory of Music. She holds a PhD in cognitive neuroscience from the University of California, Los Angeles. Dr. Viscontas has published more than 40 original papers and book chapters related to the neural basis of memory, reasoning, and creativity in top scientific journals. A sought-after science communicator, she is a co-creator and co-host of the popular science podcast, Inquiring Minds.
Many people have called the human brain, with its 86 billion neurons and hundreds of trillions of connections, the most complex thing in the universe. More complex than galaxies full of stars, or the New York Stock Exchange, or any machine that humans have ever built. It's a beautiful thing, the brain. But with all its complexity, with all its power and beauty, we have to admit that it sometimes lets us down. Take memory, for example. What were you doing an hour ago? What about last weekend? Very likely, one or two events jump into your consciousness. And for a few minutes, you can imagine yourself there, having traveled back in time, re-experiencing what was happening. Time's arrow points in only one direction unless we're talking about the marvelous thing that is our memory. That's pretty remarkable. And yet, there are many more events which seemed very important at the time, which are now inaccessible to you consciously. You might remember your first date with a loved one, but what about the second? You might remember your 16th birthday, but what about your 24th? You might have thought very carefully about where to put the keys to your safe, knowing memory is fickle, and yet 3 months later, when you need that all-important document, you search every potential hiding spot in vain. You have little control over which parts of an event you can now recall. Maybe you remember what the weather was like on that 16th birthday, but not what you were wearing. Maybe you remember where you hid your front door key, but not the keys to the safe. In fact, if you consider how little of what happened just yesterday you can still recall with any accuracy at all, you'll quickly notice how selective and fickle your memory is. And if you've ever needed to remember a name in a pinch, only to find that it completely eludes you, well, you've likely already come to the conclusion that memory is far from perfect. Why is that? After all, computers don't have this problem. Computers are really good at storing and retrieving stuff. It was one of the easiest problems that computer scientists had to solve. I mean, compared with recognizing faces, it was a cakewalk. So why hasn't Mother Nature shaped our memory system more effectively? Well, we're going to address that particular question at length in another lecture. But I bring up the problem of memory now because it illustrates a central issue that will come up time and again throughout this course. The brain is indeed a beautiful thing, but it can also be messy, random, and inefficient, prone to mistakes from the lowest levels of perception to the highest levels of complex decision-making. In short, despite its marvels, the brain is not perfectly designed. Now, this may seem to be a fairly straightforward observation, but think about it for a moment. Don't we usually act as though our brains are perfectly designed? We have great confidence in our judgments. We feel that we're beyond the reach of bias. We believe that our decisions are based on a careful weighing of pros and cons. We rely on the memories of witnesses to prove guilt or innocence. But is this confidence, this certainty warranted? Do our brains actually mislead us much of the time? How would we behave if we had a fuller understanding of all the shortcuts evolution has taken when shaping our brains, instead of living with the illusory belief that we already know our own minds? Changes in behavior will be up to you. But my goal for this course is to provide you with this deeper knowledge of how your brain actually works, not just how we think it should. So let's start by debunking the most basic myth of all, the deep-seated intuition that the brain is a masterpiece of neural design. Now, I'm not saying that the brain isn't highly complex. It is. And the fact that out of this tangle of complexity come such wonderful things as music, the Bill of Rights, architecture, and love, makes it hard to imagine that the brain wasn't carefully designed, each neuron and connection thoughtfully crafted, engineered, and assembled. But the brain is simply the end result of millions of years of evolution, and Mother Nature, with all her power, is a tinkerer, not an architect. Every complexity in our brains arose from a very long history of tiny tweaks, which, by the way, are still in progress. And some of these tweaks are more akin to inefficient hacks than to universal upgrades, fixing a bug in a computer program by just patching it up with some little piece of code, rather than recrafting the entire program from scratch. These hacks are both frustrating and wonderful. They're responsible for our sieve-like memory, the errors we make when we perceive the world, our snap judgments, but they also give us imagination, the delight of discovering illusions, and our uncanny ability to find patterns in everything and anything. Now, to understand the hacks that nature has applied to our brains, we really need to consider our path through millions of years of evolution. But here we encounter a challenge, because it's very hard to find definitive evidence for the evolution of specific psychological traits or neuroanatomy. Brains and behavior are not found in the fossil record. Brains decay and behaviors don't leave behind any traces. We can only make inferences based on what we can see, like tools and skulls and the remnants of artistic expression. But we can also look to the brains and behaviors of other animals for some answers, and to the similarities and differences between our fellow humans too. And so where possible in this course, we'll compare our mighty brains with those of other animals, and even with our younger selves. In doing so, however, we always need to keep one important caveat in mind. It's far too tempting to look to evolution for a good story and to be taken in by a compelling explanation that our minds developed just so. This type of thinking feeds the myth that natural selection had a design in mind all the while. For example, many of us watch toddlers and other little humans behave in surprising ways and fall into the trap of looking to evolution for explanations. My son's first words were car, truck, and puppy, after no, of course. Only after those important concepts were well established did he delight us by saying mama and dada. Talking to other parents, it's fun to learn that many of their boys, too, love vehicles, while their daughters are less interested in inanimate objects, but more interested in dolls or other placeholders for social interaction. So, over a glass of wine at a dinner party, we might laugh at how boys are born with a desire to get around, vestiges of their ancestral roles as hunters, while the girls navigate the members of their community, preparing the home for the return of their men. I hope that Just So story made you cringe just a little bit, because throughout this course, I hope to engage your critical thinking and show you how so many of the myths about the brain persist because they tell a good story. And stories are far more memorable for the most part than data. We might agree that evolution has shaped boys' brains one way and girls' brains another, but the inferential leap from there to an explanation based on ancestral roles is not supported by any credible evidence. And it's far more likely that these differences in preference, trucks for boys and dolls for girls, stem from our current culture rather than millions of years of evolution. Okay. With that caveat about Just So stories in mind, let's return to the question of how the pressures in the environment might have shaped the brain. As I've already mentioned, the human brain didn't just pop up out of nowhere. It's the result of a long series of small but significant changes over the course of evolution. One example of this process is our uncanny ability to recognize thousands of different faces. There's even a part of the brain called the fusiform face area that seems to be specifically designed to give us this ability to discriminate between visually similar things like faces. But chimps can do this too. In fact, they're quite adept at recognizing their friends' behinds too, not just their faces. They can quickly recognize a chimp face, but only if it's right side up, just like humans, which suggests that, like us, they process faces as a whole rather than the sum of a bunch of parts. Since primate brains changed dramatically around the same time that we started living in larger social groups, it makes sense that those of us better able to recognize faces would produce more offspring. So while our skill in being able to distinguish many thousands of members of our own species just by their faces seems remarkable and very human, it has its roots in our evolutionary circumstances, and we can see similar abilities in our closest cousins. Even dogs, bred to be our companions, process human faces differently than they do dog faces. Now, like any tinkerer, Mother Nature needs something to work with in order to tweak a species for skills like facial recognition. And when it comes to the adaptive but imperfect design of our brains, the material nature had to work with, the building blocks, if you will, were cells. In the brain, these cells are called neurons, of course. And what I'd like to do next is to examine how even our neurons point to the less than perfect process out of which the human brain emerged. Let's start with the concept of variability. Natural selection is the process by which some traits that are written into our genetic code afford some advantage to those who possess them. These lucky folks must then leave behind more children than their less gifted counterparts for the trait to proliferate. Without variability in a population, however, there's no opportunity for natural selection to operate. If we're all the same with respect to a particular trait, there's no way that Mother Nature can favor some of us over others. And so our diversity is the key to the long-term survival of our species. This variability and diversity is evident even among neurons, the very building blocks of our brains. Neurons have different shapes and sizes, different baseline firing rates, different types of connections, and different responses to the chemicals involved in cell signaling called neurotransmitters. You might remember from your biology classes that neurons have three basic parts: dendrites that receive information, the cell body that contains all the things a cell needs to survive and reproduce, and the axon that sends information on to other cells. For some neurons, the receiving end interacts directly with the outside world, as is the case in our eyes, where photoreceptors convert photons of light into the brain's electrochemical signals. These types of neurons will generally have fairly simple receptive parts. But other neurons are not so simple. For example, Purkinje cells, which are named after the Czech neuroanatomist who first described them, are found in a part of our brain called the cerebellum, and they have intricate dendritic trees. These are some of the largest cells in the brain, and they're stacked one next to the other like a perfectly coordinated marching band. What's funny about Purkinje cells is that if you look at them straight on, they have this beautiful complex network of dendrites. But if you turn the cell to the side, they look virtually flat, like a pancake. Maybe that's only funny to neuroscientists. Purkinje cells are involved in timing and motor coordination. In fact, the effect of alcohol on these cells is one of the reasons that drinking makes you slightly less coordinated, and why sobriety tests include things like walking in a straight line or bringing your finger to your nose. Purkinje cells are unique in the brain, but they still have the same roots or basic parts as other neurons. They just have more complex dendritic branching, so that they can receive a lot of information, something that's necessary if your job is to coordinate the timing of fine movements. So they're an example of how Mother Nature took the basic neuron and shaped it into a timing marvel. The morphology, the size and shape of neurons, is one variable that evolution has to work with. The length of connections, how far or near a neuron signal goes, is another variable. Some neurons send information only over very short distances within the same brain region. There's a fiber of cells, for example, one part of the hippocampus, that just feed back onto each other. Their job is to amplify a signal that comes into the hippocampus and reconstruct the details of a memory. For example, if you walk back into the halls of your high school, your mind will be flooded with memories from that time in your life as these cells do their jobs. They help the hippocampus turn a cue, like the hallway, into a full-blown detailed memory, like the time your high school sweetheart finally agreed to go on a first date. By feeding back onto themselves, they can turn a small electrochemical signal into a loud cacophony of cell firing. Then there are neurons whose axons travel from one end of the brain to the other, joining together different brain regions and forming networks that allow us to synthesize information from different senses, or use information from our eyes and ears to make decisions about what to do next. So we have this variability in our neurons, different shapes and sizes and attributes, and these differences are related to the different roles these neurons have in the brain. Some neurons distinguish colors from one another. Others power your muscles. Some are involved in complex decision-making, like deciding which political party to vote for, while others lay down new long-term memories. But hold on a minute. I've actually just made a rookie mistake in describing the functions of these neurons. I've attributed a sense of agency to them. In other words, I've implied that a neuron itself has a brain and can control what it does or does not do. That fallacy lies at the very heart of one of the biggest philosophical questions that we've ever faced. How does the mind, which gives us at least the feeling that we can control our actions, emerge from billions of cells that themselves have no control over their own actions? Here's where we turn back to Mother Nature for the answers. Both the tiny local inner neurons that turn memory cues into rich autobiographical remembering and the large, complex Purkinje cells that help you bring your finger to your nose are found in other animals, like monkeys and mice. And the cerebellum, the part of the brain that houses the Purkinje cells, has an analog in most other animals with a nervous system. So the complexity of the human brain, though impressive, is an emergent property of the many, many small changes that occurred at every branch of our ancestral tree. One type of cell that seems to be harder to find in other animals is the relatively recently evolved neuron called the von Economo cell. It's named for the neurologist who discovered them in 1929. Von Economo neurons are also called spindle cells because their cell body looks like a spindle. Each side of the cell body tapers off into either an axon or a single dendrite. This shape is unlike most other neurons that have many dendrites and projections from the cell body. Amongst primates, it seems that only humans and other great apes have von Economo neurons, and they only occur in the parts of the brain that seem to have evolved most recently: the anterior cingulate, the frontoinsular, and the dorsolateral prefrontal cortices. The anterior cingulate has a role in tracking your mistakes, anticipating rewarding things, empathy, and making decisions. Meanwhile, the frontoinsular cortex is thought to be involved in consciousness, maintaining homeostasis, your sense of your own self and your body, and your interactions with others. As for the dorsolateral prefrontal cortex, it doesn't fully mature in humans until after adolescence, and its primary function seems to be in the operation of higher cognitive functions like complex planning, flexible thinking, remembering where you left your keys, and making difficult decisions like whether to take that more stressful but more lucrative job or which college to attend. It also plays a role in deception. Some philosophers and cognitive scientists have argued that the functions of these three regions are what make us human. And because these spindle neurons are found here but not elsewhere in the brain, some have made the argument that spindle cells are particularly important in understanding the distinctive nature of human cognition. But they have also been found in the brains of whales, dolphins, and elephants. For some people, this evidence is in line with the idea that spindle cells are special since each of these species lives in relatively complex societies. And of course, it's possible that they evolved in each species independently, an example of convergent evolution, whereby the same adaptation is selected for because it solves a similar problem. In this case, maybe the problem is unique to big brains. Since spindle cells are large, they're capable of rapidly transmitting information across fairly large swaths of brain, and they seem to be especially useful for social interactions. Of the great apes, humans seem to have the largest proportion of them, but cetaceans, whales, dolphins, and porpoises have 3 times as many as humans. This little fact gives science fiction writers a good reason to write stories that feature super smart dolphins or anthropomorphized whales. So far, we've explored a few different types of neurons, Purkinje cells, von Economo neurons in particular, that seem to play roles in functions that we as humans are pretty proud of: fine motor coordination, social interactions, self-awareness. But we've also seen how they are, in fact, present in other animals, and how they might have arisen through successive tweaking of the basic neuron. In short, natural selection ended up with a hacked set of new cells, not a carefully designed foundation on which to build a perfect brain. Even so, when we consider the sophisticated way by which neurons communicate, it's once again hard to imagine how they might have evolved from single-celled organisms that were the very beginnings of life. How does a bacterium turn into a neuron? But the answer is actually pretty simple. The stuff of cells is encased in a membrane. Now, this membrane has to have certain properties, like keeping mitochondria in and keeping unwanted toxins and foreign substances out. But it also has to have an opening, or a way of letting in molecules that are desirable. Often, the inside of the cell has a slightly different electrical charge compared with the outside. In most cells, the inside contains more ions or negatively charged molecules than what's floating around outside the cell. This condition means that there is an electric potential across the cell membrane. Electrostatic forces are present such that positively charged things want to enter into the cell and negatively charged things want to leave the cell to bring equilibrium to the membrane. Now, all living cells have different concentrations of ions inside them compared with what's just outside. But neurons and some other cells, like cardiac cells, for example, have harnessed this difference for some end goal. In the case of neurons, the goal ultimately is to send a signal to a nearby cell. If you open up a hole in the membrane of any cell, the stuff inside the cell can fall out. In the case of neurons, things that are negative will leak out and things that are positive will leak in, causing the electric potential across that part of the membrane to depolarize or become less negative, more positive. This depolarization is at the heart of the way in which neurons talk to each other. Once the amount of depolarization crosses a certain threshold, it sets off a cascade of events in the cell that culminate with the sending of an action potential, or a tiny electrical signal, down the end of the axon. This signal can either be transferred directly to another cell, or it can cause another cascade of events that results in the release of neurotransmitters, the cell's signaling chemicals, into the space between one neuron and the next. So we can begin to see how any cell with a polarized membrane could eventually, over the course of many, many years and many, many incremental changes, turn into a fully functional neuron. Then, once we have one kind of neuron, the others just represent different personality types. You might be willing to accept that this type of evolution explains how neurons came about, but still have trouble seeing how little hacks could lead to the emergence of all the complexity of the human brain. It feels as though there's a qualitative difference between my brain and that of an ancestor who couldn't talk or write or contemplate her navel like I can. So, to show you how this might happen on a slightly larger scale, I'd like you to consider how self-awareness and identity develops in children. Because they're not born with the same self-consciousness that ultimately plagues their teenage years. And the process takes time and experience with the environment, not just some biological process in a vacuum. A baby is not conscious of itself or of its thoughts, feelings, and the world around it in the way that an adult or even a child is. In fact, one of the delights of parenting is watching this self-consciousness develop. I'll never forget the day my son said his own name for the first time, referring to himself. We were all so excited. What's your name?
AJ.
Yeah! It's AJ! It's AJ! What's your name?
AJ.
Before developing the intuition that he is his own person, he was largely just reacting to the world around him. But around the time that he learned his name, he started to realize that his actions can affect what his parents will do. If he throws broccoli on the floor, he's going to get the hairy eyeball from Mama. If he says his name, he gets laughs and clapping with joy. Each of these interactions shapes the wiring of his brain. In his first year of life, his brain weight literally tripled from about 350 to 400 grams to about 1,000 or even 1,200 grams. Then, from age 1 until adulthood, the size of the brain only grows another 200 to 400 grams. So most of the changes that happen during childhood that differentiate a 1-year-old from an 18-year-old are in the connections between neurons, not in their numbers. As a matter of fact, one of the signs of healthy brain development in childhood is the pruning or death of neurons that aren't finding the right connections. A neuron whose messages are sent into the void, or one that isn't receiving any signals, commits suicide. By the time a brain is fully developed, there are no neurons that aren't part of some network, because an isolated neuron dies. I find that poetic. But from the perspective of a baby neuron, destiny seems quite random. What dictates whether a particular neuron will end up as part of the visual system at the back of the brain, or the central executive in the prefrontal cortex, or the emotional salience network in the middle of the brain? The answer is in a combination of chemical signals and the scaffolding that the network of helper cells called glia builds. Neurons, of course, are not the only cells in the brain. In fact, there are about as many support cells in the brain as there are neurons, if not slightly more. This is another difference between the brain and most other organs. Many of the cells in our body are much more self-sufficient when compared with neurons, which are a bit like celebrities, needing an entourage of assistants to help them with basic functions. But their talent is in signaling and ultimately producing thoughts, feelings, and other exceptional skills that our brains possess. All cells start off the same, as daughters of stem cells, and initially, as the brain grows, changes are rapid and seem to be almost left to chance, which might be true, or it might be that we don't know what factors cause one progenitor cell to become a neuron and another to become a support cell like an astrocyte. But eventually, the rate of change slows, and neurons find their places by sending out signals to their neighbors and figuring out who's willing to talk. Those whose messages are not returned die, as I've already said. That's the micro level. At the macro level, when we're thinking about how the connections across the brain get formed, this process is magnified, but you can still see how complex cognition emerges from simpler processes. Brains develop and wire up with experience, and that's another way that diversity happens between different people and different brain regions. But this only happens gradually. To put this into context, consider the cortex, where cells are particularly open to change. They're malleable, especially in places like the somatosensory cortex, where we can measure the amount of real estate devoted to different parts of the body. Pianists, for example, have larger areas devoted to their fingers than people who don't work with their hands. Memories, whether piano skills or events in our lives, are written into the patterns of signaling amongst networks of neurons. And these patterns, and even the networks themselves, require experience to be formed. That's why experiences during the first few years of life, when the brain is rapidly developing, are so formative. The richer the experience, the more complex the connections. We can see the results of this complexity in the morphology of the neurons that develop in animals with and without enriched environments. A fish, reared with other fish, has bushier neurons with more potential connections than a fish reared in isolation. The rich environment results in a more complex cell. In a fish, imagine what's happening in a baby. far from being perfectly designed, the wiring in our brains is actually highly contingent on environment and experience, and even on how our brains were used, stimulated, and developed in the past. So far, we've talked about how our brains are shaped both by evolutionary tweaks and by personal life experiences. But there is another factor that makes our brains far from perfect: noise. Now, when we talk about noise in the brain, we're talking about randomness. For example, the random firing of action potentials. Neurons have a baseline firing rate. They send out random signals that don't actually carry meaning, at least no meaning that we've been able to discover so far. And most of the energy used by the brain goes towards maintaining the electric potential across the cell membrane so that this firing is possible. We think of the action potential as the result of a summation of incoming signals from other cells, but the truth is that action potentials are randomly fired off all the time. And the signal then, the meaningful message, is a change from this baseline firing. In other words, a huge amount of energy goes into this constant baseline firing, but the firing itself doesn't necessarily mean anything. It's only a change that carries meaning. Now, if you were designing a machine, is that how you would do it? Would you design it so that most of the energy it consumes sustains an essentially random and meaningless activity? And yet this randomness is also the base material, the unformed Play-Doh that gets molded into a mind, both by Mother Nature, tinkering over millions of years, and by our own experiences over the course of a lifetime. So no, the brain is not perfectly designed, and in many ways, it's rather inefficient. But as we'll see throughout this course, once we cut through the various myths about the brain, we find that the facts are often more amazing than any fiction we could invent. It turns out, for example, that randomness and plasticity aren't such bad things after all, because within them lies the seemingly boundless potential of the human species.